Hey guys, what's up? Eddie Alho here with KissAnalog.com. Guys, I've been looking at buck converters. I want to drop voltage down. Let's say, the common one's 48 volts, right? And drop it down 12 or 24 volts. So I've been looking for a buck converter like that, both for the video and for my own use. And so I thought, I want to do it with GaN FETs. But I don't want to use GaN FETs just for the sake of using them. I want to see if it's really more efficient. So I'm going to show you some data sheets, and we're going to go over some size comparisons, okay? And what you can do with GaN versus MOS FET. It's really impressive. So you guys, if you saw my thermal camera videos where I showed this ThermoMaster P3, really impressive camera. I've got a couple cameras that I really like, and this one you get down to those small GaN FETs. If you guys haven't seen those videos, go watch one of them. Watch the ThermoMaster P3 or any one of those, and the thermal pictures that are on these data sheets are nowhere near as good resolution because they're buying the expensive stuff that they don't have as good thermal elements. Anyway, guys, so let's jump in this video. I want to show you the difference between, and then I'm going to show you the EPC buck converter I have, okay? But I want to show you right now the data sheet between the same circuit using MOSFET versus GaN, the size difference and the efficiency. See what you think, okay? Let's just jump in this video. Hey guys, check it out. Analog Devices data sheet for this GaN controller that I wanted to show you. Now you can use it for silicon MOSFETs, MOSFETs or GaN FETs, all right? So we're going to show you both. It's a two-phase. See, it says two-phase synchronous because we have one output on the right side you see here, an inductor going to the out, but there's also this guy on the left side. So in this case, it's showing 5 volts here on the left, and over here is 12 volts. You can also put them in parallel, okay? Now, the cool thing is over here on the left, you see 4 volts to 100 volts input. Output can only go to 60, so you have to have some headroom for switching and so on. But this is a super cool chip because it can drive GaN FETs directly. You don't need a GaN driver chip in between the control chip and the FETs. So we have our two FETs here. Okay, this is our Buck FET, and this is our synchronous rectifier FET, our flyback FET or whatever. Okay, so, and here's our current sense pickup and our output. Same thing on the left side. I want to show you something. We're going to look at a sheet where they compare. Here's, look, SI FET, silicon FETs. Okay, so just a MOSFET. Now, let's scan down. I just want to show, okay, now, because of the FET they're using, and I'll show you the FET in a moment, because of the FET they're using, it's rated up to 50 volts, okay? Let's scan down here. Okay, this is what I want to show you. I want to show you this circuit, okay, the board, relative size. These are banana plugs, just give you an idea the size of this thing. Here's an inductor. Here, let's zoom in on the board now. Here's two FETs, right? Buck FET and the synchronous rectifier FET. Here's for one channel, and here's the one for the other channel, okay? So you see the control chip over here on the left, this guy? It looks approximately size comparison to one of the FETs, right? So then your output inductor. And it looks like the way they've done this is they've made it so you can put different inductors on there. I think that's why the footprint looks the way it does. Okay, so this is the silicon FET option, okay? So now I'm going to show you the option where they use the GaN FET. All right, so check out this board. All right, so here we are. Here's the control chip down here, all right? And then here's the two GaN FETs. Let's zoom in a little bit closer on that. So now look, these guys are much smaller than this. So really, two of these FETs with some space between them takes about the same area. So we have 4 FETs, right? These are GaN FETs. Now we have one of these guys. The size of this part of the circuitry has gone to 4 things this size to, say, essentially 2 things this size. So this part of the circuit has dropped in half, okay? At least half. Because they're also shorter going this way, okay? They're about 50% shorter this way and about 3 times less wide than the other FETs. So really the area they take, each one of these guys, is about, I think it's 5 or 6 times less. So that's pretty cool. But that's not the best of it. Here, that's size, right? But now let's come down here. I want to show you something else. Okay, these curves, performance curves, right? Let's look at efficiency. Okay, I'm trying to get both these 2 curves in. So you can kind of look, here's 5 volt on this side, 12 volt on this side. Now, forget about this black line because he's kind of low. Well, he's 92, right? And then all the other lines are between 94 and, say, 97, 94, 97. And over here, it's 96 to 98 and a half, 99. It's like 99's up here. So it's over 98 because the line's where the blue one is. So above 98 to right here, 96. So 96 and 98, I mean, really high efficiencies. And also the groups are pretty tight. This one down here is a little bit low. See, that's where the input voltage is 72 volts. So when you're dropping a lot lower voltage, you know, you got a lower voltage range, you're going to have less efficiency. When the voltage is closer to your output, then the efficiency is better. That's why the red one's on top, okay? Now let's go look at the other board. Okay, now this is the silicon FETs, the MOS FETs. Okay, here's the curves. Let's zoom in on these guys. All right, so here's 5 volt on the left, 12 volt on the right. Okay, look at this. Remember the black one was 92 before? Now it's what, in between 85 and 90. So 87, that's dropped quite a bit. Now, the rest of these curves, they're up above 90. So this 95, say 92 and a half would be up here in the middle where the green one is. So they're, say, I don't know, 91 to 96 maybe. And over here on the right, you know, we're going, geez, like here's 995. So this is, say, 93. We're going from 93 to, okay, if this is 97 and a half in the middle, say 97. So, and then also, and this is, I'm kind of looking up here where they're flatter, right? And you can see where they start to come up is about 3 amps. They start to level off. And over here on the left, you know, maybe 2 to 3 amps is where they curve up and they start to level off. Okay, let's go back and forth. Okay, so over here, look at this. Here's the 92%. Let's just jump back again. Let's find the 85% to see where that crossed, okay? So 85 is down here, way down here. So it crosses over at, you know, 3.5 amps or something like that. You know, this line here is kind of the worst case, but it's above 90% at about 7 amps. Go back to the silicone, 90%. Geez, this one never gets close. The next one up, 48 volts, about 4 amps it's above. So, you know, 4 amps, you're between 90 and, say, 96. Over here, 4 amps, all these lines, you're between 91 and almost 98. Not quite, but 97. I mean, it's up there. But you can see how all these lines, they always, all the rest of these, except for the black, let's exclude that for now on both of them. You come up and you stay above 94 all the way, okay? If you come over here, you stay up above 90. 94s up here. So you can see the difference, right? Now, if we look over on this side, say we go up above 95, and then they're all above 95 at 5 amps. Over here, 95 is right around in here. So let's say right here at 4 amps, we're all above 95, but we're well above. I mean, that's, you know, I mean, they're doing really well. They're kind of hanging around 97, 90, you know, right in here, right? We're over here, they're kind of more like 96, maybe, something like that. So it looks pretty close once you look over here, but you can see the difference in efficiency, right? So not only are you using a lot smaller FETs, but you're more efficient, and that's pretty great. All right, guys, so here is the Infineon, the MOSFET. So this is the silicon one, the MOSFET. And, you know, it looks typical. These are really nice FETs. Infineon makes really nice FETs. It's 100 volt, this particular one. Now, they use a different one for the synchronous rectifier. This is for the boost, okay? So I'm just showing you one of the FETs, just to give you an idea. Let's go down and look at this physical size of this, okay? All right, so this is a package outline. So this is it right here. So if we could just go to D and E, that's the main outline there. 5.15 millimeters minimum to 5.49, okay? And it can go from 5.95 minimum to 6.35. So, you know, roughly 5.5 to, so somewhere in between here, you know, we could say up to almost 5.5 millimeters by 6.35. Okay. All right, guys, this is efficient power conversion, EPC. And look at this interesting looking part, okay? Now, it's 3.5 millimeter by 1.95. So it's about 50% smaller in length and like a third as wide. So much smaller. So there you go. It's also 100 volts, 3.2. So even these numbers look better. Okay. So yeah, pretty impressive. So guys, that was crazy, right? The efficiency and the size of the GaN FETs were just so much smaller. It's crazy. Now, back in the day when I worked at DirecTV as a consultant, I was designing a power supply for the first high definition set-top box. That's how old I am. Anyway, and it was also going to be surface mount. Back then, we were all through-hole power supplies. So we're going to be all surface mount because they wanted to be on the same board as all the other electronics. So it'd be a one-board solution instead of, you know, the motherboard with all the stuff and then the power supply card. And then you have cables going between them. So get rid of all that stuff, make one card. A lot easier, more efficient design to build and produce and troubleshoot and all the other stuff. So anyway, and faster. So guys would come in and they're falling all over themselves because we're selling 4 million boxes, right? High def is like, they're predicting 250,000. But people, vendors are falling all over themselves trying to show you what they can do. They didn't even design a circuit, come in and be like, oh, what do you think of this power supply design? Just like one of your design. I'm like, yeah, pretty close. Mine's gonna be better. But they would show you how their stuff works. That's the, I mean, you know, some vendors, some places I've worked, trying to work with vendors are like, they're not that interested. But man, at DirecTV, guys are falling all over, I could have steak lunches literally every day, but you know, just vendors taking you out, trying to get your time to show you their products. Okay. So thing is I look at them and say, guys, you come out with this new FET that's like this small versus this big. And I mean, I'm just talking scale, not fit, you know, actual size, but you know what I'm saying? They would shrink a FET down to half or quarter the size, say, there you go, you'll save board space. I go, well, thing is, my efficiency is still the same. I'm going to still dissipate the same heat. So I still need to physically get the heat out of that FET. So I still need the same room on the board because the board's going to do it for me. So making it smaller, it's not really helping me. GaN FETs is different. You saw the efficiency improvement, right? So another thing that's really interesting at the GaN FET that was different than those other FETs. Now, FETs have also improved their packaging, where the thermal resistance to the board is much lower than it used to be. So that's a big improvement. GaN FETs goes another level, okay? So GaN FETs, those weird, strange-looking dies, they're like, the die is so like intimately connected to the board, the heat just is easy to get out of them, and they're so efficient, right? So yeah, you can really shrink the board space and all that, and you can change the design to operate quicker and better performance because you don't have dead space and things like that. All right, guys, I want to show you the EPC, okay? And then I'm going to show you the actual board. But let's jump into the EPC's data sheet. And they worked with Analog Device. They have the same control chip, same circuit. It's the same step-down converter with synchronous rectifier, using a FET, or GaN FET or MOS FET to do that function, right? More efficient than a Schottky diode. So, all right, guys. So now we're going to look at the EPC version and just look at their board and their implementation, okay? I want to do something maybe more like the Analog Device because I want to have a higher voltage range, and the power on either one of them is good enough for me. So, all right, let's just jump into this one and I'll show you that. All right, guys, this is the eval card, EPC, efficient power conversion. See right up here. And this is the number EPC91109, 180 watts into this. So pretty crazy, right? Here's the inductors. You can see these guys are actually very small. These are banana jacks. Banana jacks will fit in this. So you can see the inductor is not much bigger around than your banana. I mean, it's larger, but you can see what I'm saying. It's pretty darn small, right? So can you point out the 4 FETs? They're on this side of the board. There are some components on the other side, but they're on this side. Have you spotted them yet? Check it out. Let's get a little closer. All right, can you see them now? We're a little closer. I know the resolution is not very good. All right, see this guy here? That's one. Here's another. Look, there's your 4 FETs right there. All 4 of these FETs would easily fit in the size of this control chip, and there'd be plenty of space. So the components around them make these guys look teeny small. They just hide them. I mean, that is crazy. So you can see how you can shrink the size of your board by how small these guys are. All right, guys, so this is the GaN FET, okay? It's the EPC 2057. Now this is only rated for 50 volts. So in this EPC eval card, they chose a smaller voltage, so you can't go as high in the input voltage. But look how small this thing is, 1.5 by 1.2. I mean, that is teeny. There's your applications, benefits. Just show you some of the parameters real quick. Okay, we'll go more detail later. I just wanted to kind of show you the example of GaNs versus FETs. Now, guys, this is a data sheet for the EPC91109. This is the eval card, okay? 2-phase buck converter. Let's go down and take a look at it. All right, so quick start guide. You can see the top board there. There's the FETs I'm pointing to, really teeny little guys. Just want to show you this because it also shows this aluminum polymer capacitor right below these on the output. So, and there's room for a second one. So right below them, right underneath this control chip and all these parts are these parts. So this board, if you just rolled it over, you'd have this. So this is still the front, this is still the front. Let's say the back side, let's call this the back side, or this input, output, okay? So yeah, I mean, you can really crowd some small parts in there and they use lots of capacitors in parallel and series just to mostly. They use lots of capacitors in parallel to get the to get the equivalent series resistance really low, right? And yeah, pretty crazy. Now there's the schematic diagram simplified. They're not showing a whole bunch of parallel parts or anything like that. I'm gonna show you some schematics in a ramp video, and we're going to talk about the actual schematics for this. And yeah, so stand tuned for the ramp video when we go over that. But these simplified schematics just make it easy to see. Input on the left, output on the right, positive voltage on top, references, grounds below. So that's typical way we read, right? Left to right, top to bottom. So that's the way schematics are drawn. Here's our Buck FET on the top one, and here's our synchronous FET and our inductor between them. Same with the bottom, and then they get paralleled after the current sense resistors. So there you go. Pretty cool. Okay, guys, so this is the actual guy, okay? This is how it's packaged. Look at this big old box. I mean, they want to protect this thing. Here we go. We got some more paper like this down below. Okay. Our little ESD protective seal. Our ESD conductive bag. There's that picoscope. We're going to look at signals in the next video with this, okay? This video, I'm just kind of showing you the size and the difference and what you can actually get. I want to go and look at a bunch of signals and so on. Trying to see how open their fancy box. It's kind of funny. They got the top sealed, but I think I can open it from the bottom the same way because I don't think it's glued. That's kind of funny, huh? Thinking outside the box on how to get inside the box. Okay. GaN, first time, right? So there's some little demo boards are shown here. I'll bring the camera over and show you this close up, okay? Now, this is conductive, the dark ones. This is anti-ESD, the pink ones. Just let you know the difference. Conductive, so they want to have a Faraday shield. This one, they want to keep the static off of it. Same with the pink here. So that's what the pink phones and pink bags do. Just in case you know. Okay. I'm not ESD. I've been touching metal things. I haven't got cotton on me. Anyway. There's magic. I just want to show you from there. That's how small the guy is, okay? So just like the picture you saw, but I'll bring my camera over so you can see a video, of me showing you this thing. But here's a banana jack so you can plug into to do your testing. Really nice. Some jumpers that you can set this thing up different ways. But yeah, so I'll just bring it over and show it to you. That's a polymer aluminum cap, so better than the old-fashioned electrolytics, right? Because they would dry out. These polymers are more solid. They're not going to dry out like that, so they're going to last much, much longer. So I'll bring it over, show you this thing. There's actually, they got some really cool test points where you put scope tips in. So next video, we'll do that. I was going to try to make this video. It'd be long if I did the measurements and everything in the same video. So just want to show you this, okay? Let's do that. All right, guys. Hey, sorry about that. That's Texas Instruments eval card, an active clamp for it. I'm going to do a video on that too. I was just preparing for that and thought I'd do this one. So yeah, there's your inductors, output inductors, and look at those teeny little things down there. There's two there and two there. They're teeny. There we go. I guess if I turn the board over like they did in the data sheet, it'd be like that. So just give you an idea what the scale looks like and, that kind of thing. There you go, guys. Okay, guys, so I just wanted to show you this, board with the GaNs versus MOSFETs and why Now, the bad thing is soldering these GaN FETs on, even the MOSFETs, the new packages for the MOSFETs, those are even difficult. You have to be pretty good at soldering to get those down, which I know a lot of you guys are. But these GaN FETs, I don't know about that. So I'm going to have to probably get the board populated for me to use those. That's one pushback on them, I guess, is that for do-it-yourselfers, some of you guys are probably good enough to do that, but I'm not. So there's a lot of parts on that board that I would struggle with. Hey, I could get the inductors. Come on, man. Give me a break. Hey, look, I can get that polymer cap too, probably. So, no, but seriously, yeah, I'm going to do a design. God, maybe I'll just copy theirs. It's done so well. No, I want to change out the FETs, I think, for higher voltage FETs, because I want to use that full voltage range of that chip from Analog Devices supports, okay? Guys, let me know if you want to see a simulation of this as well, okay? Just say the word simulation, okay? And then that, no, I have enough volts that you guys are interested in doing that. So, and then just put a comment down and say test. If you want to see this fully tested, say fully tested, or you just want a quick test. I don't know. Let me know how deep of, I'm going to show you some, I'm going to show you some measurements on this, but let me know how you like the videos cut a little bit shorter. I better stop this video. So this one's probably longer because I showed documentation. I'm going to do a rant on schematics, okay? There's been a few things that have come up lately, and I'm like, it's time to rant. So I'm going to do a rant on schematics. What do you guys think of that? Let me know down below. Rant. Hey, hit that super thank you down there. You can buy me a beer for the rant. If somebody does that, I'll have a beer for the rant, okay? All right. It's funny. Some people get sensitized by when they see a beer on the bench, like, can't believe you're drinking a beer. Not that some people are worried about me spilling. Other people just don't like the look of a beer. Anyway, we're here to have fun. It's my bench, right? I can't wait to test this. This is a super impressive design. It just shows you what you can do with GaNs, and also with the control chip that's designed to run with GaN. That's the beauty of this one, okay? Those two things put together. All right, guys, thanks for watching. We'll see you next time.